What are the F statistics and the F test? What are the residual sum of squares form and the R-squared form of the F statistics? How do we do an F test in Stata? Hi, I'm Bob. Welcome to the 5-minute Econometrics. Today, we will explore the F statistics and the F test. The F test is commonly used to test multiple linear restrictions. They relate to the unrestricted and the restricted models. We will discuss them through a regression model to explain trichord weight in terms of various factors. You can download the dataset from the link below. It is a dataset from the textbook Introductory Econometrics, a Modern Approach, the 7th edition, by Professor Jeffrey Woodridge. The outcome variable is birth weight in pounds. The explanatory variables include the average number of cigarettes the mother smoked per day during pregnancy, the child's birth order, annual family income, years of schooling for the mother and years of schooling for the father. We start with testing whether a group of explanatory variables has no partial effect on the outcome variable. Suppose we want to test the null hypothesis that after controlling for cigarettes, birth order, and family income, parents' education has no effect on birth weight. In other words, the null hypothesis is that beta 4 equals 0 and beta 5 equals 0. The null hypothesis contains two exclusion restrictions. If the null hypothesis is true and the two variables have no effect on the outcome variable, they should be excluded from the model. A test of multiple restrictions like this one is called a multiple hypothesis test or a joint hypothesis test. To test multiple exclusion restrictions jointly, we use the F test and F statistics. The idea comes from the unrestricted and restricted models. The unrestricted model is the model that includes the two testing variables, while the restricted model is the model that does not include these two testing variables. The restriction is that the coefficients of the two variables are both 0. When the restriction holds, these two variables are excluded from the model, so the restricted model is always shorter than the unrestricted model. The idea is that when the two variables, the parents' education levels, are dropped from the model, how much will the residual sum of squares increase? If the relative increase is not large enough, then we believe the two excluded variables have no significant effect on the outcome variable. First, we should understand that as variables are dropped from the model, the explained variation becomes smaller and the unexplained variation becomes larger. Second, the residual sum of squares measures the unexplained variation. That is why it increases as some explanatory variables are dropped from the model. In other words, the residual sum of squares from the restricted model is always larger than that from the unrestricted model. Please check out my videos on the residual sum of squares for more information. Third, the F statistic equals the difference in the residual sum of squares from the restricted model and the unrestricted model divided by the residual sum of squares from the unrestricted model. It is the relative increase in the residual sum of squares when the model moves from unrestricted to restricted. The numerator is divided by the number of restrictions Q. Q is called the numerator degree of freedom. In our example, Q equals 2. The denominator is divided by the degree of freedom in the unrestricted model. It is n minus k minus 1. N is the number of observations and k is the number of explanatory variables. It's also called the denominator degree of freedom. In our example, it is 1191 minus 5 minus 1 equals 1185. This is the residual sum of squares form of the F statistic. We can also write the F statistic in R² form. The R² is directly related to the residual sum of squares. It equals the explained sum of squares divided by the total sum of squares, or 1 minus the ratio of the residual sum of squares to the total sum of squares. Using simple algebra, we obtained the R² form of the F statistic. The R² form and the residual sum of squares form are two equivalent forms of the F statistics. After we obtain the F statistic, we compare it with the critical value C that can be found in the critical values of the F distribution table. If the F statistic is greater than the critical value of C, then it is large enough to reject the null hypothesis. If the F statistic is smaller than the critical value, it implies that the change between the unrestricted and the restricted model is so small that the excluded explanatory variables do not have a significant effect on the outcome variable. We could not reject the null hypothesis. Let's compute the F statistic by hand using the formula. From the result window, we find the residual sum of squares, which is 464,041.135. We also see the R², which is 0.0387. This is the unrestricted model. Next, we estimate the restricted model by OLS. The restricted model does not have the two parents education variables. Be careful here to use the same sample as in the unrestricted model. We use the F-E sample condition to ensure the same sample size. We find the residual sum of squares of 465,166.792 and the R² of 0.0364. Now, we use the residual sum of squares form of the F statistic. The numerator degree of freedom is 2, the number of restrictions. The denominator degree of freedom is 1185, the degree of freedom in the unrestricted model. The F statistic equals 1.44. If we use the R² form of the F statistic, we should get the same result. The final step is to compare the F statistic with the critical value. The 10% critical value of the F distribution with 2 numerator degree of freedom and infinite denominator degrees of freedom is 2.3. The statistic is smaller than the critical value, so we cannot reject the null hypothesis at the 10% level that the parents' educational levels have no effect on childbirth weight after controlling for the cigarettes, birth order, and family income. In Stata, we can do the F test with the test command after we run the unrestricted model. We type test, followed by the two restrictions in two parentheses. It gives the F statistic and the p-value. The F statistic is 1.44, the same as that from the computation by hand, and its p-value is 0.238. P-value is the probability of observing a value of F at least as large as we did, given that the null hypothesis is true. A small p-value is evidence against the null hypothesis. Here we have a large p-value. It implies that the null hypothesis that the coefficients of both parents' education variables are 0 is not rejected at even the 20% significance level. The parents' education has no significant effects on the child birth weight at any reasonable significance level, once cigarettes, birth order, and family income have been considered. In the Stata result window, we find an F statistic for the overall significance of the regression. The null hypothesis is that all explanatory variables have no effect on the outcome variable. That is, all slope coefficients are 0. It is computed as the model mean squares divided by the residual mean squares. It also comes from the F statistic formula. The restricted model is the model containing only an intercept. The unexplained variation equals the total variation in this model. So the residual sum of squares equals the total sum of squares. The total sum of squares is the variation in the outcome variable, and they are the same in both the restricted and unrestricted models. This is the reason why the residual sum of squares from the restricted model equals the total sum of squares from the unrestricted model. Then the numerator becomes the explained sum of squares from the unrestricted model divided by its degree of freedom. It is 3741. The denominator is the residual sum of squares from the unrestricted model divided by its degrees of freedom. It is 392. The ratio equals 9.55, which is the F statistic. We can also obtain it using the R-squared form formula. The Stata result window gives it directly, along with its p-value. The p-value is 0 to 4 decimal places. It implies that the 5 explanatory variables in the model are jointly statistically significant at any conventional level. The above are the F-tests for the joint significance of the explanatory variables. We could use the F-test for other linear restrictions, like whether mother's education has the same effect as father's education. We type test mother education equals father's education. The F statistic is 2.52 and its p-value is 0.1126. We cannot reject the null hypothesis that they have the same effect on birth weight at the 10% significance level. Thank you so much for watching this video. See you soon on the next topic. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.